Okay, everyone. We'll go ahead and get started. I'll just keep an eye out for any additional late comers. I think there's probably 5 minutes after they can still join. And then I think the meeting locks you out. So welcome to Evolutionary Deep Learning. This is a new meetup. And it's about combining evolutionary computation and deep learning together. I've been using deep learning and genetic algorithms, evolutionary computation for about 20 some years. A lot of that has been sort of as separate disciplines. I've been very successful with using genetic algorithms and evolutionary computation for another number of commercial products, actually, during my career, for applications from engineering or simple machine learning, actually. So I thought it'd be interesting to sort of combine these things. And I've sort of pushed this out to a few of my publishers over the last couple of years, but I finally have a publisher who's grabbed me on the idea and they want me to write a book now about evolutionary deep learning. So along with my other meetup of generating reality, which has been another book that I'm almost finished writing about generative modeling, this will be another book about evolutionary deep learning that takes you through sort of the basics of what evolutionary computation is, all the way up how to use sophisticated evolutionary computation models on top of or with deep learning. Okay, so that's what we're sort of talking about today, is how these sort of things come together and how they are in separate pieces as well. And really, this meetup here is about going through the book. We might cover a chapter in an event, or might cover two events over a couple chapters, for instance, or various things. Depends on how fast we move or how people take things up. So much like the same as my other meetup, the generating reality. Okay, so what I'm going to do is I'm just going to throw up a poll here. I've never used one of these before. And so I've just put a poll here, and what I want to just get a sense of from everybody is, have you studied or previously used evolutionary computation at all? A little bit. Some you may have played with a demo, built something, for instance, you studied in university, or you perform it in your regular day job. So I see a lot of people don't have a good sense of this at all. Just inviting admitting a few other people. So most of you, it looks like, don't have any sort of background in evolutionary computation or looked at this field at all, which is kind of interesting. The reason I find that somewhat interesting is because 20 years ago, when I sort of started to learn machine learning, deep learning, genetic algorithms, and evolutionary computation, they were about neck and neck. And you'd sort of play with one or the other, and you'd have the option to use either. But it wasn't until about 10 years ago that deep learning just sort of surged ahead and became the de facto sort of top standard, where evolutionary computation and genetic algorithms just sort of fell off the wayside, and not a lot of people have learned about them or picked them up, which is unfortunate because they're actually very interesting. It can be very useful for a certain class of problems that are much different than deep learning problems, but they can also help with deep learning problems as well. So I'm just going to close that poll. Okay, thanks for that. So let's go on. So what we're going to cover in this session here is just the basics, some basic about evolutionary computation. I was sort of had a feeling that not a lot of people would have a lot of background in what evolutionary computation is, or or how it's used, or what it actually means, or what you sort of do within it. And then I noticed there's a fair number of you here with some background in deep learning. I recognize your names. So we'll just cover some how deep learning, what the deep learning, basic deep learning problems we might want to address with genetic algorithms or evolutionary computation. And then we'll talk about search in general, why it makes sense to use these types of machine learning methods to enhance our understanding of search. And then we'll look at some sort of combinations of evolutionary computation and deep learning together. Okay. So let's first look at sort of a definition of evolutionary computation. And this is just taken from Wikipedia, but it sort of is a nice succinct thing of looking at or understanding what it's all really about. There's a couple key things that come out from here. It's a class of algorithms that's inspired heavily by biological evolution. It's considered a subfield of artificial intelligence and soft computing. And it's sort of a population-based trial and error problem solver. So it's somewhat to some similar deep learning concepts or deep reinforcement learning, where you might use um, agents or agent algorithms, if you will, to sort of walk through or understand a problem. It's almost the same thing with evolutionary computation. Okay. Now, there's a whole gambit and plenty of different types of evolutionary computation. And I keep sort of throwing in genetic algorithms. That's the one that you'll typically you might be have some familiarity with, or you might have heard something about it, or played with it, or you've looked at it. We're going to look at a couple of examples that use genetic algorithms. They really are the most common thing, but there's all these other sort of different sort of classes of evolutionary computation. Everything from particle swarm optimization to swarm intelligence to gene expression programming to genetic programming and stuff like that. So in this sort of meetup series, I'll probably talk to the ones I've highlighted here in a little more detail, maybe come up with some examples or show some examples. I'll definitely have some examples that I'm writing up in the book that I'll share with you guys. Just some basic examples where you'd use these sort of algorithms to solve problems, and then how those problems actually can enhance deep learning. Okay, so really, as I said before, the basic idea is sort of a lot of this stuff is founded on evolutionary theory or biological processes. And in a lot of times, what you're doing is simulating a biological process as a way of finding an answer to a problem, or a way of performing search, if you will. Okay. So it's a typical example of how we would think of uh, a population or set of population in deep learning at its most basic form, or not deep learning, sorry, evolutionary computation, or in this case, we're looking at genetic algorithms. At its most basic form, we have the concept of a gene, which is sort of similar to the concept you might, if you're familiar with biological DNA or an RNA, it's sort of the same concept where a gene is sort of an attribute or a part of an attribute that describes something about an individual or population, or an individual itself within a population. And then what's typically comprised is we join these genes together and we call them a chromosome. And these A1, 2, 3, and 4 all represent individuals. And an individual can have one or multiple chromosomes, just like us in our own DNA. Again, we're sort of simulating the same type of behavior internally in the program, and we often use the same sort of biologically named related things as we sort of talk about them. So these are individuals, and then individuals represent a population. Okay. And here's a basic sort of premise, or the basic sort of workflow for genetic algorithms. Is we have a population that have these genes that might label some sort of attribute, and then each of these sort of are corresponding into a chromosome. And again, an individual can have one or multiple chromosomes. And these sort of chromosomes, much like us, define the attributes of the algorithm, or things about what the algorithm would do, or other attributes. Again, we'll look at some practical examples in here so you can get some ideas. From that, we typically take each of those individuals in the population, we evaluate them, and we determine a fitness value. And the fitness value determines how good the algorithm or the individual is at performing the task that we sort of have set for it. And if it's good, we give it a high fitness score, for instance. If it's poor, we give it a low fitness score. And then from here, so this box here, I'm just using a borrowed GIF from Google, had reproduction, but a better name for this sort of step is called selection. And I'll get into how selection works in a second here. And then crossover, which is more like reproduction, and crossover is where the sort of genes come together and combine. So typically, male female reproduction, 50% from the DNA is from the male, 50% from the female. Sort of the same idea. There's a lot of variation here that we'll play with, and some other ways we can look at crossover, but that's the basic idea. And then there's mutation. So there's always a chance of, after something's sort of joined, there's always a chance that something might mutate. So one of those genes might flip or do something like that. Okay. So here again, when we think of evolution or evaluation or fitness, here's an example of a genetic algorithm running sort of a walking character through multiple individuals. And you can see the best fitness individual is the one that's sort of reaching the farthest, and it's identified as the highlighted character. And the fitness in this example might be how far the character can make a certain distance. And if the character can make 100 units or 100 meters, it has 100% fitness, where if it's only making 1 meter, it only has a 1% fitness. This is the way we would think of fitness. And then that fitness sort of plays into how we might do selection and some other things later on. Okay. So typically in selection, we have multiple different forms of selection. And selection is sort of like mating, or you can think of it as sort of the precursor to reproduction, if you will. So typical selection might be, the top, you might have elite selection or elitism, where the top groups of individuals from each set, or you might separate your group into two sets of individuals, and the top most pairings of the groups, or the most performant or the highest fitness individuals combine, and so forth. Or you could have round table or roulette wheel, I guess I should say, or different rank and order. So you might actually take the least fit and the middle fit and combine them and do some other sort of variations. This is where you have a lot more flexibility than you would in sort of a biological model, where you can choose a lot of different variations in the type of selection you use for how you're combining your sort of your individuals. So you can, there's lots of times where, you don't always want to pick the highest performing individuals, because that highest set of performing individuals might be following a path that gets them to a local optimization, but it's missing the global optimization, where other individuals might be better suited to find that global optimization. Sort of the same thing we might encounter when we're doing any other optimization problem, where we're finding local or global minimum or maximum. But in this case, by having that variation, you're allowing sort of other individuals to find other routes or paths to those things. So it's a little bit different than using, say, optimization in deep learning, where you're always sort of looking for that one path. You're taking multiple paths in this approach. Okay. So reproduction and crossover is where we're joining two sets of chromosomes or multiple sets of chromosomes together. And here's an example where we might have parent one and parent two. And parent one, we're taking a subset of these four genes here, and then we're going to splice them into this section. And likewise for this one, we're taking these and we're joining them, and then the offspring might look like this. And that these values here, the FGH, or they could be numbers, or they could be anything really, could represent everything from drawing a triangle a certain area, or it could be, in genetic programming, it could be an operation, for instance, or it could really be anything. You could think of it as describing anything. In deep learning, as we look at later, it could be actually just, certain values of weights, for instance. Okay. So as we get to certain levels, we'll either decide to run a simulation for a number of generations. And so each time we do a loop through the process of, mating, reproduction, mutation, and then generating a whole group of individuals, that's essentially one generation. And we might do 100 generations, 1,000 generations, 1,000,000 generations, for instance. In this example here, you can see the first generation little dinosaur is just falling over. 20th generation is still failing, but around the 999th generation, we look like we have a stable model. Sometimes it may work like that, sometimes it may not. It's a lot of it's how well you're distributing things across problems across the space. And that all comes down to a lot of what the selection mechanism is, so how you're pairing up your individuals and how well they're sort of diversifying, and then how well you're tracking fitness and how well things are making it across. And then if you have enough individuals, and you don't typically need a lot of individuals, you typically run with maybe 100 individuals, which is quite a bit different than deep learning, when you might require millions of training iterations or other things like that. Okay, and then mutation. So this is sort of a typical mutation operation on a small sort of chromosome here, where we have this section of 3 genes here that are essentially just flipped, and that might be the type of mutation, or the mutation could really be anything. The mutation could be something self-customized. You could have it say mutate from, maybe it increases something up or down or whatever. You might not necessarily have this might be a true or false sort of attribute chromosome. You might have something more sophisticated. You might have multiple levels. You might have 10 or 100 different levels that could be different attributes of one particular gene. You could have repetitive genes. You could have a sequence of genes that need to rely on one particular thing. There's various different ways of sort of combining these things. So there's a lot of flexibility here. Okay, so what I like to always do as I go through these things is to give people some sort of tangible grasp on how these things come together and some cool examples. So one of the first things we'll look at here is basically originated from, I think this has been around since about 2003 when I started playing with it. This came out, I think, in MSDN magazine as a C# example, and that code example is, I think, been buried in and out of places. I think I finally actually found a project. I'm not sure if it'll run, but this has actually been converted to a website. So what I'll do is I'm just going to take, oops, I think I actually have it on the website. So let me just stop the sharing, and I'm just going to share my browser. So here's the website. Let me copy the thing in the chat window for everybody if you want to sort of follow along. Okay. So this has been adapted, I think, from that original C# code. I think it's probably running in JavaScript or something like that now. And what you can do is you can select a number of images here. So, and I'm sharing the right screen, right? Yeah, nobody's complaining, so I'm assuming I'm doing well. Okay, so I'm going to choose something like this cartoon character, for instance, right? So if I click Start, what's happening here is essentially we're creating populations. And the population in this example here from the controls is we're sending it up to 50 individuals. And those 50 individuals are essentially the genes that represent or are represented here are essentially the 3 points that need to describe that polygon. And there might be, I think in this particular case, we're looking at 125 different polygons. So there might be, you can think of it as 125 different chromosomes, or there might be one just big long chromosome that has 125 spots that represents where those 3 points are. So that's essentially what the genetic piece looks like. But all we're doing is taking that stretch of genes, and for every iteration, so what we've done here is probably loop through a number of generations of individuals, and you can see as we do, it gets closer and closer to this individual. And the fitness for these things, or the fitness test, is it's doing a pixel-wise comparison to see how well the colors or how well the image lines up with each other. And we can see as the individuals get better and better, and we're using this sort of these selection cutoffs and these mutations and all these other modifiers, we can see how these will change the way or how quickly these things learn, or how well they learn, for instance. And this is a really good, interesting example. You can, choose a Mona Lisa, or as I looked at before, Tom Waits. So if I stop and start again, you can see that, black and white images are obviously a little easier to learn. But there's a lot of interesting things you can do and look at, and this will really give you some basic understanding of how these things work, and it'll give you a little more understanding of how these controls work. So the population is what we talked about, is the number of individuals we're throwing at the problem, and the number of individuals we're sort of playing through the problem at every point. What we're seeing here that's being drawn currently is probably the best individual or the fittest individual. The selection cutoff here is based on, I'm not even sure, well, it might say here what selection it's using, but changing that selection cutoff might be, I think the selection here is that the top 15% are the only ones that mate into the next round. And then it might be sort of random selection after that. So you might want to increase that. You might want to make it, like maybe the top 20% can mate or the top 25% can mate. And then you can also change the mutation chance. So the mutation chance typically will keep very small. And we usually limit that amount of mutation over the number of individuals, so we don't get a lot of strange things happening. But this might be around from 1% or 0.5% to 5% is usually a typical number. But, and then you can modify the number of polygons you're using, etc. The one I think I generated in the diagram in the thing was over 12 hours or something like that. So you can see it can do really well short term, but then sort of long term, it gets a little difficult depending on the complexity of the problem. And that's something with genetic algorithms that we'll sort of look at here. Maybe a downside of them, but in some ways a benefit. Okay. What I also want to look at is another website. So I'm just going to copy this. So here's another example, and this is sort of modeled after the TensorFlow one, where you have these things, the ability to set these things right here. So you can set the number of generations that you want your individuals to sort of run through. You can set the population, so how many individuals you want, the selection type, and the selection, so it's either elite, so it's either the top individuals, or it's tournament, so it's sort of like, well, we won't get into that, but or roulette, and then the crossover percent, so how much of each individual is crossed over, or what percentage is crossed over, and then there's that mutation percent, okay? So in this case here, if I just click run, in this problem, you can see this is sort of the 8 queens problem. It's, how can we arrange 8 queens on a fixed chessboard such that none of them share the same row, column, or diagonal? So that's the problem we're looking at here. So let's see how long genetic algorithms can solve this. And it's solved. So you can see in this problem, we sort of optimized that it'll stop early once it reaches 100%. So once it finds a solution, it stopped. And from here, we can see that it's automatically stopped quite quickly. I can look at something a little more complicated, maybe the traveling salesman problem here. So in the traveling salesman problem, the problem is that we propose a fictional salesman that's going to be visiting all these destinations, but he wants to do it in the most economical way possible, such that as he's sort of visiting each of these destinations, he never reverts back to his path. And so he can make a simple path all the way through all the destinations and then return home when he's done. Okay, so let's try and run this. Again, we got a little different numbers here. Generations 200, population 50. We're doing a different selection. The crossover and mutation, I think, are quite similar. So let's just see what this looks like. So after about 200 iterations or generations, it's still up to about 60%, but you can see it's coming up with a reasonably good solution. I mean, if we reduce the number of cities here to 10, we could probably see a quick resolution. Yeah, still only reaching about 60%. I'm not sure why, but so the really good example of that, and that's really something useful to play through. There's a couple other examples here as well. So yeah. Okay, so, and then another cool little program, if you're used to working with a lot of sort of tabular data sets, you're typically doing a lot of data science, those types of things, and you want to sort of look at a different way of solving your problem than other machine learning models. There's this thing called gene expression programming. So gene expression programming is essentially based on genetic algorithms, except it takes it one step further, where instead of building these genes and these chromosomes which are hidden inside the model, it's actually developing a computation that can solve or functionally solve across the data or learn to optimize against that data. So for instance, if I look at this problem of concrete strength, and it has a number of sample problems, and this package is called GeneX Pro Tools. Probably not a lot of you have looked at it, but it's based on genetic expression programming. It's been around for about 15 years. I use it sometimes as sort of a way to look at other data science problems or tabular data sets or other things. I think there's a 30-day free trial if you want to take a look at it. But it's kind of cool. So here's the model. It's been trained. But what I can look at here is, so if I run it, there it is. Go ahead.
You're still showing traveling salesman, so not the.
Okay, thanks a lot. Yeah, it doesn't allow me to share my screen for some reason. Okay, let's try that. Okay, so this is the GeneX Pro Tools. It comes with this sort of nice little interface. What I'm doing is I just let me just go back here. So what I did is I just looked at one of the example problems. So there's a number of different sort of problem sets that you can look at that if you're interested in solving these things. So there's a regression set, logistic regression, classification, time series, or some sort of logic synthesis. So I'm just going to look at the concrete strength example. It's already open. Okay. And what you can see is sort of different plots here. And you can look at this and understand this on your own. The primary plot here is the fitness plot. So it's telling you how fit your individuals are. And the other plot here is the how well it's sort of performing on the model. So I haven't really I just sort of trained this a little bit. You can see it's after a little while, it's already gotten about 70% accuracy, I guess, or 700%, 700 fitness. Not sure what that means, but let's just look at the results or the model. So what this is generating is actually it's generating code. So that this process is actually generating code that you can use in a model that you've trained through this gene expression programming tool to do whatever computation or calculation to find your answer. So as a regression model or classification model, and you can use lots of different languages. You can use Python, you can use other languages. And I found this tool very useful for smaller data sets. If you only have like less than 100 samples sometimes, and you're sort of struggling with machine learning models, this is a really great tool to sort of look at those types of smaller problems where evolutionary computation, genetic algorithms especially, perform quite well over that space. Okay, let me remember here to stop sharing, and I'll go back to the PowerPoint. Was there any other questions? I know I'm covering some of this stuff always fairly quickly, but no? Okay. Okay, so there's that other package. Oh, the regenerate. Oh, yeah, okay. Well, you guys can play with that on your own. The concrete strength problem in that tool I showed was, it's just in the tool. It's one of the example data set it's in the tool. And that tool, again, is GeneX Pro Tools. I'll just write it in the chat window. Okay. And here's an example. So we looked at sort of the GeneX Pro tool, but the idea here is it's really a subset of evolutionary computation. You can almost think of it as a subset of genetic algorithms where it's genetic programming, where we're actually deriving equations in a certain form or set. And here's an example of a tree-based genetic program that's developing this sort of functional program based on how the individuals train. You can actually develop programming code that could do some operation or stuff like that. There's lots of examples or models that are around that'll do that for you. The GeneX Pro tool does an example of genetic programming where it's doing actual, it's trying to combine the symbols or functions, and you can actually customize your own functions that you want to use in the code, or how it calls those functions. So it's really useful or interesting that way. Okay, and there's that GeneX Pro tools. Okay, so what are the benefits over deep learning? So what are the benefits of genetic algorithms, evolutionary computation over deep learning? Well, they typically really perform well over smaller data sets, where deep learning shines on larger data sets or understanding a whole sort of global domain rather than a smaller subset of domain. And I often get asked by people, how many images do I need to train a deep learning system? Well, it really depends on the size of network you need to learn the data, which then drives the number of images or the number of data that you need for your model, right? The larger models need more data. Whereas in evolutionary computation, you don't necessarily have that restriction. You can use very small sets of data or small sets of individuals to train over your problem. And they can become quite good, and they can search through larger search spaces, again, based on whatever selection mechanism you use. And that's sort of your tuning mechanism for determining how well it searches over that search space. Okay. The other big thing is that these types of models don't get hung up by discontinuities in data or cross-domain conflicts in data or stuff like that. So here's on this side plot here, we have an example with a graph of lots of discontinuities. If we were to throw this at a deep learning problem, it would have a fit trying to solve it. It just wouldn't be able to solve it, right? But with genetic algorithms, it can very much or very readily solve these types of problems because it's not affixed to using calculus and backpropagation to find some optimization for the function. It can actually find its own function. And especially with the genetic expression tools, you can have if then else's in your essentially equation. So you can have, Boolean logic and other things. You can actually have really, expanded discontinuities in your data, and it can account for that. So it's really nice that way, to be able to manage across those problems that we often see in deep learning. Okay, and it's not prone to function collapse. It's another problem we'll see with deep learning, where you get this problem happening with vanishing exploding gradients, where your network becomes too big by the time it gets to the middle or the end. The number is either so big or so small that it becomes really difficult to train any sort of effect later on or down the model. This doesn't again happen with evolutionary computation. It doesn't suffer from this problem. And it's typically a better generalizer. Evolutionary computational models are typically a better generalization, which is something we often struggle with in deep learning models, because deep learning models can become very specific quite quickly. And this genetic algorithms sort of are a better generalizer, I guess you could say. They've sort of better attune themselves to the whole problem rather than subsets of it. Okay. So why no hype? Well, a big part of this is that genetic algorithms are computationally expensive, and they take a while to run, and there currently is no GPU options. But that doesn't mean to say there couldn't be GPU options. That doesn't mean to say that somebody writing the TensorFlow framework couldn't add a GA module on top that just sort of piggybacks on top of the tensors that we're using for the deep learning model, that allows us to perform some other GA tasks within the deep learning model itself. This space, though, is really new as far as combining these things. So it's probably going to take a couple more years before we're seeing any of that, but hopefully soon. Okay, and it really handles large variable spaces somewhat poorly. And I'll get into this when we talk about search, but it handles sort of narrower spaces better than deep learning in some ways. Okay. And the other thing you have to realize is that random becomes important. So as much as you can see your you can see the loss going down or stabilizing with the deep learning network when you're training evolutionary computational models. It could just be one individual that gets unstuck or untrained that all of a sudden spikes your model, and then you continue from that point. That's sort of a very different thing from if you've done a lot of training of deep learning models, is that you get a much different approach to training because you're not getting that sort of wobbly effect, or not so much, but you can get spikes in fitness where the fitness will increase and then the model gets better. And it's often those spikes, where you get almost like a different species of individual, you could say, that you get those really big changes. And the other big thing here is really evolution and diversity are still a little sort of delicate subjects for some areas of the world. And I used to think, creationism and all that stuff was just a small subset of people until I started traveling to Texas every week for my one of my former jobs, and realized that no, there's actually a lot of people that do believe in this stuff and wrestle with these concepts with, also dealing with religion. I think the typical way they frame these things now is based on the cartoon, is that evolution was here, it happened, and then God came after. I'm not sort of trying to bash anybody's religious views, but it is sometimes a sore spot, sometimes a thing to get over. It's still in some areas of the US where they require evolution and creationism to be taught side by side, which is, I don't understand how that works, but anyways. Okay. So I'm just going to throw up another poll here. Oops. It's not letting me pick my other poll. Let's see. No, it's not allowing me to. Not allowing me to grab the other poll. Okay, no, that's fine. We'll just keep going through here. But if you think you'd need an introduction to deep learning, yeah, if you could just throw yes or no into the chat window, that'd be helpful for me. Okay, so I'm seeing a few people would like some refresher on deep learning. Well, we're not really going to cover that right now. I'm just going to go into the rest of my presentation, but it'll be something I'll consider for later or future events for sure. Okay, so let's just talk about the problems of deep learning itself. So deep learning is the best, but a few of the bigger problems are, especially for newcomers or people learning, is the hyperparameter tuning. It's time consuming, especially if you're training complex models. It can be error prone. If you're changing values and you forget which value it is, or your notes are wrong or stuff like that, it becomes error prone. It requires a fair bit of discipline because you have to break down your variables and keep training those. You have to make sure that it's all spot on kind of thing. You're often confined to continuous functions. As I mentioned before, deep learning is only really at the peak right now, only doing most of our continuous problems. That doesn't mean to say that it doesn't change in the future. A lot of people working in deep learning are looking at that very problem. Often limited to academic search. And what I meant by this point is that often when we're expanding or learning new models or undertaking these things, it really becomes down to the academic realm that's sort of building these things and sharing these things. There's not a lot of wiggle room as far as individuals making progress on their own in deep learning. And this often takes sometimes multiple universities getting together to make really big contributions. So, companies like Google or other subsets of things, they're making progress, but they often publish things, and a lot of their individuals working within the company often are, working at academic universities or so, and sort of sharing the research as well. And then as it's sort of coming right now, not for some things, but models that are in the deep reinforcement learning realm, for instance, are really becoming over-engineered. Without getting into specific details of that, I mean, really, really detailed. as far as what needs to go into the model. In some deep reinforcement learning models, you might have 5 submodels within that model. Some of them are critiquing what the agent is doing, and critiquing what the agent's doing one step ahead or multiple steps ahead or other things. So it's really getting complicated as far as some of these systems, the way we're building them. Okay. So really it comes down to the space of deep learning problems and search problems. And what we're talking about often when we look at these, combining these things or understanding these things better, is it really comes down to a search problem. In the case of hyperparameter tuning, we're really searching for what those parameters are. In the case of training a network, we're looking or using backpropagation as a search mechanism to find the weights in the network. To finding new ways to either define the loss in a network, or defining new network architectures itself, or even actually simplifying the network architecture. So all those things are search spaces that tons of academics and other people are working on all the time, but really, none of it's sort of optimized. Everybody's sort of doing their own thing, I guess you could say, and it often doesn't really sort of narrow down to your particular problem, I guess is a real point of interest. Okay. So really, when it comes down to search, who does search the best currently? Really, what we've seen is, and this is a fairly recent plot, is we sort of have random search down here, and then reinforcement learning, which is done really well, and I'll get to that in a second. But then we typically see for evolution on sort of the front end, evolutionary computational models are really typically better and can outperform reinforcement learning at doing search in the space it's well at doing search at. Even you could even get into larger models, I guess, but the problem, I haven't played with larger models because the computational power. That doesn't mean to say in the future, if we're using GPUs or something like that, where we're using a whole bunch of individuals, or we're looking at a whole bunch of generations, for instance. Okay. So here's an example of reinforcement learning doing what it does. It's gone from AlphaGo, where it solved the problem of Go itself, to AlphaGo 0, where it learned how to solve the problem of Go just by training itself, to AlphaStar, whereas that was the version of the reinforcement learning version that beat the real-time strategy game, and then AlphaFold, which is just something that came out quite recently, where they've released a model that can learn how to fold the proteins. And this, if you read the articles, is a 50-year problem we've been searching on, a really big search space problem. And I think they most certainly have tried genetic algorithms on it, but as I've mentioned before, the search space is just really, really large, and this is where reinforcement learning does quite well. Okay. So when we talk about evolutionary search, and I typically say it's well suited to small and medium spaces in practical applications is what I'm talking about. And one of the things that Charles Darwin wrestled with when he came up with the fundamental concept of evolution was, he looked at minor changes and seen evolutionary changes in birds and stuff like that, the fit of the bill or the wings or stuff. What he sort of wrestled with when he was dealing with this theory was the problem of an organ like the eye. And when you think of the eye, which is a very complex mechanism, how does it derive from just doing minor changes over a period? And that's the problem he wrestled with. And sort of why he always came back to, and he was a very religious man, he always came back and said, well, maybe God only took it so far, and then evolution's taken over since, is one point his thinking. But what we've learned since is, using some models to train on and looking at studying nature, is that sure enough, even complex structures of the eye, and here's an example where in this right side here, this is an example that's trained genetic algorithm model that's trained to build the eye, and I think it was over 500,000 generations, which is quite a bit, but it's still doable. And in terms of evolutionary or our evolution, it's certainly doable, right? 500,000 generations is certainly doable. It's a drop in the bucket. And this is sort of an example of the eye forming in various mollusks. And you can see the evolution of the eye there. So there is very, evolutionary computation it is limitless. And it can do lots of stuff. It's just throwing how much computational power we have at it, and if there's ways to optimize that, I guess is what we're looking at now. Okay. So how can we combine evolutionary computation with deep learning? So we'll look at a few examples here, and one of them is hyperparameter tuning. And as I explained before, hyperparameter tuning is a really problem set for especially, a wide range of deep learning developers, where trying to find the parameters to tune your model, it's error prone, it's problematic, it's people just don't want to do it. They just want to have their model sort of built out of the box. To replacing back propagation, so it allows our deep learning models to learn outside of and to learn discontinuous data, to finding new architectures or loss functions, to full integration with this thing called NEAT. I'll get to that in a second. So here's an example of hyperparameter tuning. So we have a number of hyperparameters up here, and these might be the appropriate values you set for that various hyperparameter. And you can see they're, especially in the learning rate, we're setting it, I think, increments of 0.001, for instance, but you might change variations on that. And this is the way that sort of the loss is going through and changing as it's going through the model for your different settings on your hyperparameters. And you can see this is really complicated as far as setting this stuff up. Being able to do this with genetic algorithms where it's automatically doing it for you would be fantastic. So that'll be an example we'll look at in the series of events in this meetup. Okay, to replacing back propagation. So there's no reason why we couldn't set up, a chromosome for each layer in this model for an individual, and then each of these sort of weights here represents a gene, and then use that to train a set of individuals to not use back propagation at all in a deep learning model as a way of finding the parameters inside the model itself. So that's another problem we'll look at in this series. To actually finding new architectures themselves. So you can, encode the architecture of the model in some sort of genetic encoding, and then find whichever architectures works better for your problem by adjusting that. So either changing which type of layers you're using in a model, to how many neurons are in that layer, for instance, or other things. So we'll look at a problem like that in this as well. Okay. And this is sort of an example of just a whole sort of deep learning model for computations, but actually finding new loss functions. So when we're doing generative modeling and various generative functions, a lot of the times we tweak the loss functions over various ways. What we'll do in this part of one of these events here is actually finding ways of using things like gene expression programming or other genetic programming operations to find different loss functions that you might train a model over. Okay. To NEAT, and NEAT stands for Neuro-Evolving Augmenting Topologies, and this was developed in about 2003. Like I said, these things have been around for quite a while. In Austin A&M University, where the principal idea is that NEAT does everything. So it essentially adjusts the model, trains the parameters, and adjusts some of those hyperparameters. Okay, and it's a package in Python that you can actually use and build right now, and you can train it on things. And we'll look at that as an example. So here's an example of NEAT being used in a game. And what you can see here is the number of generations and the number of species, genomes, and stuff like that, what the fitness of the model is. But what's underlaid here is actually what the structure of the network, what the deep learning network looks like. And you can see that structure is changing based on the individuals and the iteration or the generations it's moving through. So each game it might play through, so each individual might play through one iteration of a game to derive its fitness, and then that fitness of that model is used to sort of, the selection, reproduction, mating, and then generating new individuals. So, okay. So why evolutionary computation for deep learning? Well, as I said, the deep learning problem space is really optimal for evolutionary search. It's really that narrow set of problems that that really work well for evolutionary computational models. So it really makes sense. Okay, it's sort of a reset from the over engineering that we're sort of doing now, or this sort of overemphasis on building bigger models or making these models more complicated. But a lot of times we're just building these models out, big layer here, big layer here, big layer here, big layer here, and we're not really optimizing any of the middle pieces, right? And this is where we get into problems with um, exploding and vanishing gradients, because our models are either becoming too big, we're not training them well, we're not pruning them well. And this is where, introducing evolutionary computation as a method of pruning those models and reducing them would really make sense in this case. So that's another piece we'll look at. Okay. And computational search is really hitting limits. Now, the GPUs, I think, are still on track to follow the 1.5 times doubling for the next 5 years. But I think after that, we're sort of hitting physical limits that will come to a point where we'll be limited to that, and we'll have to look at other problems. And this is really setting it up well to evolutionary computation being that other set of things that can wrap around these models. And another big thing is that reinforcement learning is a really fantastic model algorithm, and it's really great at doing search, but it's often considered brute force search. And what they don't often publish in these papers with, hey, this is a really great breakthrough. But, for instance, I think the AlphaGo, if it was trained on a regular computer, it would have taken 45 years for the computing power of that single computer to be able to train AlphaGo. So 45 years nonstop training. So reinforcement learning is really computationally expensive, and that's why we need to look at other methods that sort of can reduce that sort of need to really just throw power at it. And reinforcement learning is really throwing a bunch of power at a problem and looking at all the search spaces, and we could probably do a lot better than that. Okay, and I'm just being sort of blunt here. It just makes sense. And getting back to the old Jurassic Park movie and the comment, life finds a way. Well, life found us, evolution found us. So why does it not make sense to give this a try as far as augmenting it with deep learning and seeing how well that can enhance these models and carry them forward? Okay. So any questions or comments, thoughts or ideas? Yeah, so they've used, I think there's actually in that website I shared with you, there's actually a production scheduling problem, or there's a scheduling problem. So the question was, can we use evolutionary deep learning for production scheduling? Well, you can actually use evolutionary computation for production scheduling. And you could just look at that website and it might give you some ideas. I think there's a scheduling example in that website that can show you, but definitely evolutionary computation could help with that, yes. Very, like I showed, the traveling salesman problem is a good example of that. Yeah, so the PyTorch seminar I did last week, I think is what you're meaning. I didn't record that one, but we'll be holding a bunch more of those as well. For this one, this series will be done in PyTorch as well with Python, using for deep learning. For the genetic algorithms, we'll be using a problem called DEEP. It's called distributed, DEEP and GEPI. So GEPI is another gene expression programming tool in Python. There's a few others around. But that's sort of the frameworks and models we'll be using. Okay. Any other questions or comments? Yeah, feel free to unmute. I think you guys can unmute as well. Thoughts, comments, nothing? Are all of you Python programmers here? Sorry, Simia.
A bit of it.
If you could just answer yes or no in the window, if you know Python. Yeah. Okay. Good. Go ahead, Sunil. Sorry to cut you off there.
Um, Earlier, we began saying that EC is more computationally intensive than deep learning, right?
Well, so, and what I meant by that is it's everything you're going to do with evolutionary computation right now is going to be CPU based. There's no GPU stuff that can offload that, make it faster. So it will be more computationally intensive. Yeah, that's what I meant. Does that answer your question?
You mean to say by combining um,
Yeah. So by combining so the deep learning models will look at, and even using, for instance, Google Colab or something like that, the deep learning models will run on a GPU, but the EA models will run on the CPU. So they'll sort of work in tandem together, I guess is what I'm saying. But what I mean by they're computationally intensive is they can take a long time to run, essentially. Um, the processing power may not be as much as, say, a deep learning model where you're actually going to be using a lot of computational power. It just might take a lot longer to run, I guess. Maybe that's a better way to say it.
so won't the total time taken to arrive at a solution be the weakest link in the whole thing as well?
So that like I said earlier, a lot of the times when you're training models or you're training individuals in a population, in deep learning, or even other machine learning mechanisms, you'll see a gradual, a gradual loss, or some minimization of what your answer is, and you can get a sense of maybe you're coming to an answer soon. In genetic genetic algorithms, you can get the same thing, but oftentimes you might get a jump. An individual, like one of the individuals, might find a different way of doing things where you get a jump, and then the fitness sort of scores there and it goes. But sometimes you'll get a fall back as well. So it's a little bit like machine learning, but in some ways, if you have the proper selection mechanism, you can find some really late bloomers, I guess you could say, where they sort of all of a sudden they jump out of nowhere and they actually solve the problem. And you'll kind of see some of the same things in reinforcement learning, but with evolutionary computation, you'll see some of these where all of a sudden it'll spring to the solution, for instance, really quickly. It again depends on how well you're sort of how big your population is, how much diversity you have in your population. Well, I'm just trying to speak in generalities and abstractions, but we'll look at, so the next event, we'll probably look at some actual building some models and looking at some problems. Go ahead, Abdul. Any other questions or comments? And kind of a full circle thing here. The image is from a movie called Life Story. It's either called Her Horizon.
Hello, Michael.
Go ahead. Go ahead, Partha. Can you hear me?
Hello.
Yeah, we can hear you.
Hi, I'm pretty new to this meetup, and kind of was quite impressed by your presentation. Do you have previous other once in a month?
We'll probably do this meetup every 2 weeks because there'll probably be a lot of content to cover, and I'll probably want to cover it fairly slowly. Some of my previous meetups probably covered content a little too quickly, so we want to cover a little slower so that you actually have some working experience with these things. I think is more practical. I think for people to learn.
Thank you. My connection is not all that great, but I just try to be with you guys. Thank you.
Okay, thank you. Okay, guys. Any other questions? Can we work on some of the Kaggle problems? Yeah, if you have any problems you want me to look at or play with, throw them my way. We can definitely include them. As an author, I have to be a little careful on some of these things. So I often avoid Kaggle or other sort of competition platforms. If it's on GitHub, though, with a license, it's generally I can take a look at it and modify it and do stuff. Okay. Okay, guys. Thanks everybody for coming out. And everybody have a great holidays and a happy new year. Thank you, everybody.